Hey folks, the Earthlings. Welcome to Decoding the Earth, the podcast where we dig deep into the layers of our planet to uncover the fascinating stories beneath our feet and sometimes even above our heads. I'm your host Raihan Ghani, a geologist and professor here to bring the rocks to life. Each episode will explore how geology shapes us by shaping the world around us. Ready to decode the earth? Let's rock. If you have ever checked your bank balance before making a big purchase, you already understand today's episode. Because the United States has a water account too, and most of it is hidden underground. We can see lakes and rivers, but groundwater, the water stored in pores and fractures beneath our feet, supplies drinking water, keeps farms irrigated, and helps streams keep flowing during dry spells. The trouble is, it is out of sight, and what's out of sight is easy to mismanage. So, here's the big question. How much groundwater do we actually have, and how deep is it, right where people live and make decisions? A new hyper-detailed national map is giving a clearer answer than ever before. Measuring groundwater isn't just for scientists. It's water security. If you don't know how deep the water table is, you don't really know how expensive a new well will be, how vulnerable your supply is to drought, how quickly contaminants from the surface might reach drinking water. At a national scale, missing that picture makes it harder to plan irrigation, conservation, and water infrastructure, especially as climate extremes intensify. For years, large-scale groundwater estimates were often inferred indirectly from broad data like rainfall and evaporation. Useful, but imperfect, like guessing your savings by watching what you spend without ever looking at your statement. Reed Maxwell, a hydrologist at Princeton University, has a powerful analogy. He says, rainfall, snowmelt, and surface water are like checking account, money that moves fast, used for short-term needs. Groundwater is the savings account, the reserve you lean on when times get tough. And his warning is simple. We often don't know how much is going into that savings account, and we don't know the balance. That's the groundwater problem in one sentence. Researchers at Princeton University and the University of Arizona tackled this by going straight to the source, wells. They assembled more than 1 million direct groundwater depth measurements from across the US. Then combine those point observations with the regional climate and geologic information. Next, they trained a machine learning model using a random forest approach to estimate water table depth everywhere between the wells and even map uncertainty. The result is striking. Groundwater depth mapped across the contiguous United States at about 30-meter resolution. That's neighborhood scale, not the blurry kilometer scale view we have often had before. And it is not just depth, it's volume too. The team's estimates add up to roughly 306,000 cubic kilometers of groundwater, more than 13 times the volume of the Great Lakes. This also connects to satellites. Missions like NASA's GRACE can sense big continental changes in water storage. But there are two cores to tell you what's happening in a specific valley or farm field. The new approach helps bridge that gap, using well measurements to build a detailed picture that complements what satellites see from space. Now for the number that made me sit up. About 40% of the contiguous United States has a water table shallower than 10 meters, and about 16% is shallower than 5 meters. Why is that important? First, access. Shallow groundwater is really cheaper to reach, critical for rural communities and agriculture. Second, connection. When groundwater is close to the surface, it can interact strongly with streams, wetlands, soils, and vegetation. In many places, that shallow groundwater helps sustain plants through drought and supports base flow, the background water that keeps a river alive between storms. Third, vulnerability. The flip side of being close to the surface is being more exposed. Land use, fertilizers, leaking septic tanks, and industrial contamination can matter more when the water table is shallow. In other words, shallow groundwater can be both a lifeline and a liability. Here is the practical payoff. You can't manage what you can't measure. This kind of high-resolution groundwater accounting can support smarter irrigation planning, more targeted groundwater protection, and better drought response because it identifies where groundwater is likely to be accessible, where it is likely to be deep, and where uncertainty is high. And the team isn't keeping it locked in a paper. They're making the outputs publicly accessible through open platforms like HydroFrame. So the next time you look at a river, remember that visible flow is often fed by an invisible partner beneath the ground, water moving through sand, gravel, and fractured rock, our hidden savings account. This has been Decoding the Earth. If you enjoyed this episode, share it with someone who cares about water, because the future of water is going to depend on geology, data, and a whole lot of good accounting. Until next time, stay curious. A special thanks to Professor and Geologist Nahid Gani for directing and producing this podcast. Don't forget to subscribe and follow us on social media to stay up to date on all things geology. See you next time on Decoding the Earth.